Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the 19th lecture of the course Maritime Structures, which is offered by Swayam Prabha in the Department of Maritime Engineering, IIT Gandhinagar. In this lecture, we are going to extend the discussion what we had in the last lecture on curved beams. So it's a sequel lecture on curved beams 3, where more details will be now discussed of curved beams with large initial curvature. So friends, if you look back the last lecture, which I want you to please look at that before we continue this, the last equation we said is E of del d phi by d phi integral over area A y plus E by y plus r of y dA was equated to the applied moment m. We designate this equation as equation number 11. Okay. So, I think you are back with that. If you are not, please go back to the previous lecture and land up here and understand that this equation is done. Okay. We proceed from here now. Having said this, Let us now pick up this integral. The integral y square plus ye by y plus r of dA over area A need to be evaluated, is it not? Okay. In simple terms, let us do the synthetic division. So, let us say I will rewrite this as y square by y plus r of dA over area A plus E times of y by r plus y of dA integral area. Okay? I split this integral into two parts. Let us pick up I1 and expand. I1 is, let us say, I want to divide y square by r plus y. Am I right? See here, I want to divide y square by r plus y. So, let me perform the synthetic division and say, let us say this is y. So, I get r y minus plus y square. So, then I change the sign, this cancel, I get minus r y. So, now I can write this integral as y minus r y by r plus y of dA. Can I say that? I performed synthetic division and I computed this as I1 now. Okay. Now I can write integral y dA over area A minus r integral y by r plus y dA over area A plus, we already have the second term here, I am borrowing it there, okay, plus E times of integral y dA by r plus y over area A. Okay, that is my integral now, total. We already know integral y dA over area A will be 0, assuming that the geometric axis coincides with the neutral axis. Okay. So, this term can be set to 0, right. Therefore, integral y square plus E y by r plus y of dA over area A now can become minus r times of integral y r plus y dA, is it not, this term, plus E times of integral y dA by r plus y of area. Okay, friends. Now, we already know that integral y by r plus y dA over area A is called as MA. We already said that in the previous derivation. Previous lecture, if you look at that, we already have this equation with us. We know this. So, what I am going to do? I am going to substitute this as MA here and here. Okay, let me do that. So, now the integral becomes minus r MA plus E MA, where MA is the modified area. Okay. So, that becomes minus MA times of R minus E. I call the equation number 12. I substitute equation 12 in equation 11. Please do this. So, that will give me minus E times of d phi by d phi of MA R minus E is M. Please be careful in writing, this is modified area small m, this is applied moment capital M. So, do not get confused with these two terms. Okay. Don't mix them up. So now I can say E times of del d phi by d phi is equal to minus m by m a r minus e. Can I say this? Okay. So this is derived from here. Going to the next step, substituting from equation 9 the previous lecture. Okay. E del d phi by d phi is m by a. Equation 13. Now substitute this in equation 4. Let us see what do we get. Stress is going to be m by ae y plus e by y plus r, which is equation 14. Now I want to write the above equation in the form of m. So we already know that E is m by m minus 1 of r. Therefore, stress is now m by a r m minus 1 by m of y plus m by m minus 1 of r by y plus r. I have just substituted. Okay. So now I am writing this as m by a r m minus 1 by m of m minus 1 y plus m r by m minus 1 y plus r. So now I am saying I cancel this. Okay, this is my stress. So what do we get? Stress is going to be m by a r 1 by m of let us say m minus 1 into y plus m r by y plus r, which is m by a r 1 by m of m into y plus r, okay, minus y by y plus r. Now I can write stress as m by a r, okay, 1 minus, because this whole term m gets cancelled and y by r is 1, right. So 1 minus 1 by m times of y by r plus y. Can I write this? I call this equation number 15. Is it okay, friends? Please have a look at this. Okay. Having said this, so I write this equation again. The stress is now given by m by a r of 1 minus 1 by small m of y by r plus y. Okay. So this is called Winkler back equation for curved beams. Okay. Let us explain this, where sigma is the stress in the cross section, okay, is either tensile or compressive at a distance y measured from the centroidal axis, that is very important. We do not measure the distance from the neutral axis in this equation. Okay? Be very careful about that. Y is measured from the centroidal axis, where m is the applied moment, has a specific convention, opening curvature, closing curvature. A is the area of cross section. Small m is section property, and of course, r is the radius of curvature of the unstressed beam measured to the centroidal axis. To use this equation, let us see what sign convention we require. Okay, let us see the sign convention to use the Winkler-Bach equation. Y is negative when measured towards the concave side. Just to reiterate, this is my curved beam. Okay. This is the concave side and this is the convex side. This is my neutral axis, this is my centroidal axis. So, this is my centroidal axis, this is my neutral axis. If I measure y towards the concave side, then I say it is negative. Okay. So, with this sign convention, stress is positive when it is tensile. Okay, that is very important. So, sign conventions for C equation should be remembered, be very careful about this. Okay. Having said this, we now know stress is given by m by AE y plus E by r plus y. Okay. Now, we can modify this stress in a different form. Let us say I have a curved beam of a specific cross section. This is my center of curvature O. Okay. This is Ri intradas, this is Ro extradas, and if this is my centroidal axis, then this is R, correct? So, if you look at this carefully, I take any fiber and I measure y, the distance of the fiber. If this y is measured towards concave side, it is negative. If you look at the derivation carefully, the PQ fiber was measured this direction, right? That is why it was taken as positive. Okay. Now, if I have the neutral axis marked here and the neutral axis shifting towards the intradas, this shift we mark as E, is it not? Eccentricity. E is the shift of the neutral axis from the centroidal axis, correct? Is measured towards the intradas or towards the center of curvature, towards the concave side. Okay. With this, I can write now stress in intradas, this is the point intradas, is given as m by AE will remain as it is. Now, I want to write, let us say I am measuring y towards the concave side from the central axis, right? From here I am measuring. So, what should be this value? What should be this value if I measure towards this? Can I say this as E minus HI? Because you know the nomenclature, we already said the nomenclature. Let us draw the nomenclature again. So, from the centroidal axis, this was indicated as this was indicated as HI, correct, from the centroidal axis, and this was indicated as HO, right. So, I am writing that. So, E, I am retaining E as it is. Since I am measuring towards the concave side, I am saying this Y is minus HI, okay, that is what I am trying to do, okay, divided by R minus HI, am I right? So, which I can say now as minus M by AE of HI minus E by, if I say R minus HI, R minus HI, can I say this is RI? I can say this is RI. So, this negative sign indicates that it is compressive. Okay. That is a convention we already had also. If you look at the stress distribution, so when you apply, when you have a curved beam, when you apply a moment this way, you know these fibers will be in tension and these fibers will be in compression. So, as you move towards intrados, these fibers will be in compression. Okay, clear? Now, let us do the other equation where I am going to say sigma O outrados, extrados, okay, or extrados now. So, it is going to be M by AE. So, let me write the equation first, Y plus E by Y plus R. So, I rewrite this equation as M by AE, okay, E, I am moving towards the convex side, I should say HO, see here, when I move from here towards here, it is HO, that is Y value. So, I have written Y value as HO, let me write it here clearly, let me rub this, let me write it clearly, HO divided by, if I say Y plus R, now R is here and this is Y. So, can I say this value as RO, or let us say R plus HO, which now becomes plus M by AE times of HO plus E by RO. This plus indicates it is a tensile stress. Okay, friends. So, I got two equations which have been subdivided and classified for intradas and extradas separately, which are derived essentially from the Winkler-Bach equation providing nomenclature. So, friends, we look at both these equations, I am writing them both in general equation, let us say. Stress is given by applied moment by AE Y plus E by Y plus R. This is general equation. So, in this equation, we know M, capital M, this is an applied moment. Okay, we know this value. We know area of cross section, we know radius of initial curvature. We can, if you want to find stress at any point Y in the fiber, which Y will be indicated wherever you want to find, okay. If I know the value of E, can find stress. So, what is E? E is the shift of neutral axis from the centroidal axis, is it not? So, I should be able to find out E from the geometry of the cross section. Okay, that is the idea. Friends, let us try to extend this discussion further. Let us say, if I increase the radius of curvature to a very large value, let us say curved beams with large initial curvature, and become a straight beam. When R tends to infinity. Okay. In that case, what will happen to my stress value? Then in that case, stress should be simply m by I into y, no? That is the equation for the straight beam. Is it not? Equation for straight beam. Let us check that. Let us check this. Stress for the curved beam is given by m by AE y plus E by R plus y. We know E is minus mr by 1 minus m. So, therefore, stress now becomes m by minus m a r times of y plus E into 1 minus m by r plus y. I have substituted. Okay. Now, for a straight beam, what is the shift between the neutral axis and the geometric axis? The shift between the neutral axis and geometric axis, which is actually given by E, is it not? Is practically 0, is it not? In straight beam, the neutral axis and geometric axis will coincide. So, E will become 0. Okay. So, when E becomes 0, m is also 0 and R is infinity, that is what the condition is. So, when E becomes 0, m, the modified property, modified area property, that is m also becomes 0 and R tends to infinity, that is how the curved beam becomes a straight beam, and hence what will happen to my stress value, which is minus m by minus m by small m a r of y by r plus y. That is what I will get. Okay. Further, we know y square dA by integral r plus y is said as y minus ry by r plus y of dA. Can I write that? Can you see this? Simply y square dA by r plus y, okay, can be written like this, which we just now proved. So, if this is the case, and we also know y dA is set to 0, hence minus r integral y by r plus y of dA now becomes minus r of ma. Therefore, stress now becomes minus m by mar y by r plus y will now become stress m by integral y square by r plus y dA y by r plus y. Okay, which now becomes my by 1 plus y by r of integral y square dA by 1 plus y by r. When r tends to infinity, stress now becomes, friends, m by I into y. So, you know, the curved beam essentially becomes a straight beam, because we know I, where I is integral y square dA, is it not? Second moment of area, which is applicable to straight beams. Therefore, friends, M, which is a sectional property of a curved beam, need to be evaluated or estimated for different cross sections. Because MA is called the modified area. Now, we will pick up different cross sections and try to work out this modified value. Let us start doing this from a rectangular section. Let us pick up a rectangular section. Let us mark the values. I say is my center of curvature O, let us mark it as O. Okay. I will mark the CG, centroidal axis, at a distance R from the center of curvature. Let us say the breadth of the section is B, and from the center the values are h by 2 and h by 2. The total section depth is h. Okay. So, let us say this value is R1, that is intradas, and this value is R2, that is extradas. Now, I pick up a strip at a distance V from the CG or from the center of curvature. Let the thickness of the strip be dV. Okay. Let us say this strip is measured at a distance y from the central axis. That is a general thing what we did in the derivation also, same figure. Okay. Now, dA, the elemental area, is given as B dV, and MA is given by integral y by r plus y dA, which is now said as y can be written as V minus r. Can you say that? And r plus y can be said as V and dA, which now becomes integral dA minus r times dA by V, okay, which now becomes we now say integral dA by V from R1 to R2, dA by V from R1 to R2 can be said as B dV by V R1 to R2, because dA is known to me. Now, I can write this MA as A minus, because you know this integral will become A, okay, minus R into B natural logarithm of R2 by R1. Can you say that? Because this is dV by V, which is log V, Substituting the limits, I get this, which is said as A minus RB ln of R2 is R plus H by 2 and R1 is R minus H by 2. Can you say that from the figure? If I know MA is so much, I can now write E as MR by M minus 1. Okay? Okay, before that, let me remove this. Let me write M is equal to 1 minus R by A times of B natural logarithm of R plus H by 2 by R minus H by 2. Can you say that? Then I write E as MR by M minus 1. So, I have M, I can substitute here and I get E as E is going to be 1 minus R by A B ln R2 by R1 by 1 minus R by A B ln R2 by R1 minus 1. So, this goes away. Therefore, I get E as minus A by B ln R2 by R1, okay, plus R, okay, plus R. So, if I know the value of E, I can locate the neutral axis from the central axis. Okay, I can locate the neutral axis from the central axis easily. So, this is for the rectangular section. Let us learn it for a circular section. Let us learn it for a circular section. Let us draw a circle. Let us make it bigger. Let us say I mark the central axis from the axis of curvature the center of curvature. Let me mark this distance as R. Let me mark the neutral axis at a distance E from the neutral axis, from the central axis. Let us cut a strip at a distance R at an angle theta, and let the thickness of the strip be dy. Okay. Let us say this strip is marked at a distance V from here, and let us call this as dy. Okay. Now, with this reference of the figure, we now write the following equations. We know MA is given by y by r plus y integral dA. Am I right? This we already derived. Okay. So, from the figure, if you, okay, this is also called as y, also called as y. So, now we can say y can be said as v minus r. I can now say this as v minus r by v dA integral, which can be integral dA minus r dA by v. Okay. Now, let us see what is dA for this figure. dA is going to be r cos theta, please pay attention to this, r cos theta into dy, 2 times of this, that is what is y from this equation, from this figure, is y equal r sin theta. So, then what is dy? It is r cos theta d theta. Therefore, dA now becomes 2 times of r cos theta, then r cos theta d theta, which becomes 2 r square cos square theta d theta. So, integral dA by v will now become integral 2 r square cos square theta d theta by r plus r sin theta, as v is r plus y and y is r sin theta, right. So, now I can say this is going to be equal to integral minus pi by 2 to plus pi by 2, 2 r square cos square theta d theta by r plus r sin theta. Okay. So, let take a constant k as ratio of r by r. So, integral dA by v now becomes 2 r square by r of minus pi by 2 plus pi by 2 cos square theta d theta by k plus sin theta. Okay. I can now write this as 2r times of minus pi to plus pi by 2, 1 minus sin square theta by k plus sin theta d theta. Okay. Let us do synthetic division of this. So, let us say 1 minus sin square theta is divided by k plus sin theta. Okay. I will say minus sin theta. So, that becomes minus k sin theta plus, or sorry, minus sin square theta. I change the sign, it is cancelled. I get 1 plus k sin theta. Okay. I add k here. So, I should say k square plus k sin theta. I change the sign, gets cancelled. I get 1 minus k square. Therefore, I can now write this integral as 2r times of minus pi by 2 to plus pi by 2 k minus sin theta plus 1 minus k square by k plus sin theta d theta. Okay friends, I am rewriting it again. So now the integral becomes 2r minus pi by 2 to plus pi by 2 k minus sin theta plus 1 minus k square by k plus sin theta of d theta, which now becomes 2r times of minus pi by 2 to plus pi by 2 k minus sin theta d theta minus 2r times of k square minus 1 by k plus sin theta minus pi by 2 plus pi by 2 d theta. Okay. Now, what I will do, I will take this as a separate integral, this as a separate integral, and I try to calculate them. So, please do this homework. So, if I do this as I1, which is actually this integral, okay, which will be actually equal to two r times of k theta plus cos theta minus pi by 2 to plus pi by 2, substitute them, I get this value as 2 pi r k. Okay. Now, I take the second integral. I take the second integral I2, which is integral minus pi by 2 to plus pi by 2 k square minus 1 k plus sin theta d theta. Okay. So, this integral will give me the value as if we simplify and integrate, it becomes 2 by root of k square minus 1 pi by 2. Okay. I want you to please check this. Okay. Now, substituting back, I will get this equation. Substituting back, I will get m as 1 minus 2 r by r the whole square plus 2 r by r root of r square root of r by r square minus 1. Okay. So, I get m. Once I get m, I can always find E as m by m minus 1 of r. So, friends, as a summary, in this lecture, we learned the Winkler-Back equation for curved beams, the Winkler-Back equation for curved beams of large initial curvature. We have also learned how to find the stresses at intradas and extradas of the curved beam. We also find the modified area properties MA for two different sections, rectangle and circle. We will do this for furthermore in the next lecture. We will do some example studies in the next lecture. Hope you have followed the lecture and the derivation. Please rework it again. If you have any doubts, please post it to our discussion forum at Swayam Prabha. Instructors will be able to reply to you, support you parallelly. Thank you very much. Namaste.